Hello, so this talk is about how we use R in Eurocontrol in my unit, where we do performance review of the service providers like air traffic control centers in Europe. We do it as part of the Eurocontrol, which is the European organization with 43 member states going from Armenia to the east till Portugal and the oceanic side, and Norway and Morocco and Malta to the south. We are having 32,000 flights in Europe per day as of May 2019, and something 4 million flights per year. We do this to check the emission of CO2 or efficiency of flights, number of flights in airspaces, and how air traffic controllers are being used, trained, and the cost associated with that. We do this also to disseminate data via a portal which is built with Blockdown. We try to go towards the right of this graph, so being fully transparent and reproducible, trying to put not only the results of our analysis, but also the input data, the methodology, and the software. We have been producing a few packages where we try to put all the code that we use, and we are doing more and more. The last one is the trajectory package, which is analyzing trajectories. If you think about them, they are simply 3D positions time-stamped, and we need to do this kind of analysis to find out which airspaces they are intersecting, where flights are staying. We can read different formats for trajectories, from radar reports, segment-based ones. We can do plots geographically, so on the horizontal side, but also on the vertical profile in time and space. This allows us to visualize what we are investigating. And of course, we are also extracting data from the databases that we have. This is an internal feature, but it allows us to expose the data for our reports. We have, so we can export trajectories, but also airspace structures, which is basically polygons extruded in 3D between flight levels. In terms of airspace, the most difficult part we are dealing with is intersection between these trajectories and airspaces. SF as such is not usable for us because it is mainly 2D. So, and if you have loops like holding patterns above airports, like in Heathrow, like in this picture, when we have to analyze holdings in the holding areas, or SF doesn't work. But our code allows us to extract the level pieces of flights, because these are inefficient pieces of trajectories that lead to more noise or more fuel burned. So we are doing this analysis covering all airports in Europe, all the major ones, and we analyze the ones that are performing better and getting feedback to the airports, but also to the airlines, so that they can improve their efficiency. We do this analysis also on traffic delays to show the causes of delays, which can be weather, we cannot control, but we can control the number of positions of air traffic controllers, and so this can improve the way of managing the airspace. We also, density plots for, this is from ADSB, and the next revolution for us is the availability of crowdsourced data as position transmitted from aircraft. So we want to put these trajectories out in the open to be able for everybody to scrutinize what we do, but also to have new ideas. So if you have questions and you want to get in contact, have a look at our GitHub organization. I've put links, or get in touch with me, and let's start the conversation.
Hello, my name is Piotr. I'm going to show you a presentation related to measuring inequalities from space. This is just a short overview. A full tutorial can be found on my GitHub account. On 2 slides, there is a link for that, so you can get it. Basically, this data can be useful for measuring market potential or development level for areas which are scarce of official statistics or not administrative units. I'm working in the University of Warsaw. I'm also heading a small group of data science enthusiasts, and this is one of our projects. We are using this data from satellite images to measure development for areas which are not smaller than administrative areas in here. Basically, the data which we work on come from satellite images. They are collected by NOAA. The globe is divided into pixels of the size less than 1 square kilometer, which for each pixel there is a measure of night light intensity in so-called digital numbers. And there are 2 types of data. Initially, there were annual summaries. Since April 2012, there are monthly data for night light time intensity available. Basically, these data are very useful as they are independent of politicians, independent of statistical offices. They are uniformly measured across the whole globe, and they can be easily aggregated to areas which are different from administrative areas where official statistics are not available. That's why they are quite popular proxies for economic activities, but they can also be used in business to measure market potential. And there's a lot of research based on that, which shows a strong relationship between nighttime lights and GDP or population at a national level. But on a regional level, this relationships are much weaker, which requires some additional adjustment as the relationships are not linear. And I'll show you a few examples based on the data for 2013. For the whole globe, for world countries, for EU countries and regions, and for US states. Here, just few slides, but the full analysis is on my GitHub, as I said. So the analysis requires a few steps. The first step is importing the data, of course. We need raster data, which is well managed by the raster package, and spatial data, including maps, which will be overimposed on the data from space. There is a wonderful package SF, which most of you probably know. Then we need to check and adjust the data, to check the coordinates projections if they fit to one another. We need to check if the regions' geometries are valid. I explain it shortly in the tutorial what it means. So if these data are correct and fit to one another, then one should limit the data to this area, which is analyzed to make the raster data smaller and therefore to analyze it easier. There are specific functions in the raster package which allow to do it, crop, mask, and then we can aggregate the data to administrative areas or any regions which we define. Usually the sum of the nighttime light intensity is calculated for every region. To make it efficiently, I suggest using the package tabular raster, which allows to index the data, which makes the calculations much faster. And here you see the example correlations between GDP and population for EU countries. It's quite high, up to 0.9. The national level is very strongly correlated, shows very strong correlations, while on the regional level it's much weaker, as basically nighttime lights underestimate the urban areas, right? So there is a different pattern of relationship between for urban and rural areas, and that's why correlations are much weaker on the regional level. When you perform this analysis for US states, it appears that the correlations are again quite strong, as strong as for European countries, up to 80%. Sometimes log linear relationship is found. That's why I also collated correlations for a log of lights, but they are much, they are slightly weaker in most cases. So to sum up, R has great tools to analyze such data. They can be used to measure market potential or development for areas which do not have official statistics or which are not administrative areas. And if you wish to play with this data, you can find a full tutorial on my GitHub. Thank you very much. And
Hello, my name is Florence Carpentier. I will present you here our package Silent for spatial inference of landscape that we developed with Olivier Martin at INRA. The problem when you are estimating the spatial inference of landscape is that you have to estimate the intensity, but also the scale of effect, and that is often difficult. I will consider the case where you have some variable, often an ecological variable of interest that you have measured at different locations, and you have a landscape that is a set of geolocated variables, such as polygons for fields or forests, or segments for edges. And the idea is that Silent is a user-friendly tool from data importation to map results. And it will permit to estimate at the same time the intensity and scale of effect. So we consider two models. The first model is a buffer model, where we model the landscape influence in disk around each observation. And the problem is to estimate at the same time the effect and intensity, but also the buffer radius, so the buffer sizes. We can also consider different type of observation, like polygonal observation. In this model, we consider that the landscape effect begins at the borders of the fields. So I had to wait. As you can see, first you have to import your data, and this is very simple with only two code lines, one for the data, the observation data, and another one for the landscape data. And then to estimate the landscape influence, you can write the model in a LM-like syntax and add the results using the summary function. There you can see we have a negative significant effect of the first landscape influence. I don't have a pointer, but at large scale, and a positive effect significant for the second variable. When we consider polygonal data, the results are quite different. With only the second landscape variables that have significant effect and with larger scale. We can also map the results, and there you have the results for the point data with a negative effect at large scales and no significant effect for polygonal data. And there we can also map the result for the second landscape variable. And then you can see the buffer estimated for the two models. So with very short distance scale of effect for the point data and larger scale of effect for polygonal data. The second model we consider is based on what we name the spatial inference function, SIFE. The idea is to discretize the observation on a grid and consider that each point of the grid has an influence that decreases with distance, and we modelize these influences using the SIFE function. Knowing the location of the landscape variables and the SIFE function, we can compute over all the landscape the influence of the landscape variables. So the idea is, the aim is for us to estimate at the same time the intensity of effect of each landscape variables and the parameter of the SIFE function of each landscape variables. We can do this using the function Silent, which had also an NM-like syntax. And using the summary, we can have test and estimate of effect. And we can also map the effect of the first variable on the left, the second variables at short distance, as you can see, and the global effect of the landscape with negative zone of effect, positive zone of effect, and also neutral zone. So Silent is available on CRAN and our GitHub page. It's a project that's still in progress, so do not hesitate to contact us if you have any questions, suggestions, or comments. Thank you for your attention.
Good morning, everyone. My name is Annette, and I'm going to present how the Marine Stewardship Council is navigating the spatial data with a combination of R and Python. So this has been teamwork of the whole team that's shown below. And I'm in charge of the spatial database that I'll show you now. So in general, the MSC, you probably know the little blue label that's sometimes on seafood product. That's the MSC, the Marine Stewardship Council, and it's certifying marine worldwide sustainable seafood since 1997. The mission is to safeguard seafood for this and the future generations, and they're using the market demand instead of the pressure from the fishing companies to accomplish the goals. So how do we get the data at the MSC? We get, so we have the fisheries, the auditor, and the MSC, and the fishing companies have to pass reports through the auditor to the MSC, and from these reports we can extract our data, and when the report is handed in, the fishing companies get the certification if they accomplish everything. So we have two kinds of data. We have the, the certification data, that is big database, and that's stored in a data warehouse, and that's accessed through Excel and sometimes R. And then we have the spatial database that is accessed through R and sometimes Python. So usually the marine stewardship data looks like that. So we have lots of point locations of fisheries all over the world, and then we can do different spatial analysis on that. So for example, on the one side, the catch data, or then doing some density maps. So that's the kind of stuff we're doing at the moment. Now we're moving to the spatial database that's including polygon data. So that's fishing, the red areas are the stocks, that's where the fish is. The blue areas are where the fishing boats are, and when they overlap, the fishing boats are catching the fish. So this is the data we want to work with. There's different user groups at the MSC. It's a quite particular setup because it's a big organization, so you have very different levels of software and coding proficiency. So you have the licensing and chain of custody outreach team, that's the green users, that's the biggest user group, and they are normal software users, so they can't code, they can't do anything like that. Then we have us, who can code, who don't like the click software, so we have to find something in between. So the normal spatial database is held in Postgres SQL, and then we use R and Python to import the spatial data, so the fishing areas and the stock areas, into that spatial database. Then we use QGIS, that's publicly available GIS software, as a graphic interface. So this green user group can access QGIS through the built-in functions or custom QGIS plugins. And then we have the intermediate group that can code a little bit. They can access their data through R, either through their own code, that's at the bottom, or through code that they can use through QGIS that is pre-coded through us or by them. So how does that work structure-wise? So we have QGIS that can access the PostgreSQL spatial database, and that can be accessed, as I said, directly from the green users. Then we have R that can be accessed through the users who can code. And we have a package that's called RQGIS, and that enables us to access QGIS Python geoprocessing functionalities from within R. So you don't need to use the actual Python, you can use R, but access these functionalities in QGIS. And then, of course, we can code custom plugins. And all of this is sometimes used, for example, to do analysis like that. So when we have, when we try to match fishing areas with attributes with external spatial data layers. So these are global data layers with big fishing areas, for example, defined by the United Nations sometimes. We can overlay these and see if a fishing area overlaps with specific United Nations areas, or if sometimes we can also create a buffer around fishing companies and see how that all works out. So we have to do that through Python to enable users to run these scripts, but without knowing Python. So this is work in progress. It's working out well so far. If you have any questions, we are available on Twitter, of course, through the MSC, but I'm also available to answer questions by email, or when you see me around, feel free to ask questions. Thank you very much for your attention, and over to the next slide.
I'm Kim, and I'm a civil servant for the French National Institute of Statistics. During this presentation, I will quickly present some R package on how to deal with the change of administrative divisions over time, and I will do it in the case of French territories with some of my R package, initially in French, that I translated for this presentation a bit in English. So in France, there are lots of administrative divisions that fit into each other. This is what we call the French territorial millefeuille, which is the cake at the top left of the slide. The smallest are the communes, the municipalities, and the biggest are called the régions, at the bottom of the slide. These administrative divisions change over time. Here you can see in blue the French municipalities that have gathered with other ones during the last 50 years. And a small number of them have also separated in pink. This evolution of municipalities is tricky when you want to compare data produced at two different dates. Here are some R functions to deal with this evolution issue. The municipality evolution graph gives you, as you can guess, a graph of the evolution of a municipality. Here you can see that the municipality number 76,108 gathered with the 76,095 in 2012. And finally, they decided to split again in 2014. You can guess the year of a database with the OGC guess function. Here we have the database DB, which corresponds to the number of men and women in each municipality in 2016. And the merge OGC function shows you the difference between your list of municipality in your database and the one of what we call the official geographic code. The main issue is to change the year of the geographic code of your database. For example, it is useful when you want to compare two different databases produced at two different dates. Let's imagine you want to change the geographic year of a numeric variable. If two municipalities merge together, it's simple. You just have to add the two lines. And if one municipality split into municipalities or more, you just have to, for example, divide lines proportionally to the population of the new municipalities. If you want to change the geographic year of a typology, for example, urban versus rural municipalities, the rules for the transformations are different, but I won't detail it here. Here we use the change OGC numeric functions to change the geographic year of the database DB from 2016 to 2019. Because of the many mergers between the 2 years, you can notice that the number of lines was first 35,900 in 2016, and now is less than 35,000 in 2019. As I said, the administrative divisions fit into each other. So using the aggregate OGC function, you can aggregate the database DB of municipalities into a database of the 101 French departments. With this function, the number of men and women of each municipality are added for each department. And as you can see on the bottom picture, you can then map, for example, the proportion of men in each department. I will now conclude by talking about some improvements that could be interesting in the future. My first goal will be to create some new functions for the package. For example, the possibility of adding our own geographical levels, or our own distribution keys, divide proportionally to other variables than the population, for example. After that, I will be also interested in expanding this thinking into other countries. For example, using what we call in Europe the nuts. Finally, this tool is also interesting for non-R users. This is why I'm thinking about developing Shiny apps and maybe API later. Thank you for your listening. The two packages I used for this presentation are called Conjugaison for the functions and Cartelette for the map layers. You can find me on Twitter and GitHub, and I will be pleased to have a discussion about dealing with the change of administrative divisions over time in France or everywhere else.
Hello. So I'm going to present you a new package called Persephone, which is still under development. And it deals with hierarchical time series in R. So basically what we do is we wrap some functionalities from the JDemeter package, which is recommended by Eurostat for time series adjustments, and build some additional tools on top of it, which deal with hierarchical time series, so multivariate. And we try to visualize them and get some neat diagnostics where really every component can be viewed individually. Currently, this package is only available on GitHub, so interfaces might change, but its grand release is planned later this year. You can, of course, install it with the remote package and the install GitHub command. So about the basic syntax, this package allows to basically convert time series objects into so-called Persephone objects. And those Persephone objects can then be used with several methods. For example, the run method, which invokes the Java backend to perform the adjustment. And then we can use the object to retrieve the adjusted time series. And of course, other components. Here are some plot types that can be produced with this package. The first one is actually an interactive graph. We don't see this in these slides, but they can be zoomed in and out using some mouse gestures. And there we see the original time series as well as the adjusted one. And the trend curve. We also have several plots related to the distribution of residuals and autocorrelations of these figures. So now about the hierarchical models, which is actually the focus of this package. So when I talk about hierarchical models, I mean that we have time series that can be broken down into several components. A typical example would be a price index, where we have prices of different goods which are aggregated to a price index. And those aggregations can have several steps, so they are like a tree-like structure. And we try to delegate the adjustments down to the several components. And in order to do that, it's currently the only way is to use a syntax which is similar to a named list, where we can combine several Persephone objects into one hierarchical Persephone object. And when we run it, it will just delegate down to the several components, and the print method gives a nice overview about where seasonality is still present and about the outliers. The plotting method for the hierarchical series are still very simple. So here we just see the original series, the adjusted series, and the indirectly adjusted series, which are not very far apart. So it's almost not visible that those are actually two lines. But we will add some functionality to also see how the components evolve and how they evolve differently from the aggregates. Other plans for this package are to generate the Eurostat quality report, which is normally generated by the JDemeter Plus package, and to generate it in a similar manner. Also to give the possibility to create dashboards to get more overview about the different components. These slides, as well as the package, can be found via GitHub pages on the Statistic AT site. Thank you.